We are going to be doing a new section today, chapter 16.3. It's got a very important heading or title, Fundamental Theorem of Line Integrals. Well, anything with the name fundamental is probably going to be pretty important. I think the last time you've seen the term fundamental, wasn't it the fundamental theorem of integration, which basically said if you want to find the area under a curve, you know, from A to B of some function f of x, that it was f of b take away f of a, right? We're going to find that there is an analogous version of that for line integrals, but that's still to come. Before we do that, I need to get us used to some skill building. Suppose I have a function, right? Just a normal function x of y. Excuse me. And I tell you that the partial derivative of f with respect to x is x cubed, and that the partial derivative of f with respect to y is y squared. And I said to you, find a function f of xy where this is true. Excuse me. Okay, that's a brand new question. I don't think we've ever had a question that looks like this. So imagine you're the first people tackling it. It has to be a single function that both of these things are true, right? Excuse me. How do you think you might approach this question?
Take the integral of each side and add them to each other, because since there's an x in one and only a y in the other, then if you add them together, they should cancel each other out when taking the derivative.
Interesting. So let me take your thought process. So if I wanted to find f, I'd basically integrate this guy, right? What you said. Well, with respect to x, that's quite easy to do. Would you agree it's power rule plus c? But here's the difference. In normal one-dimensional world, right, these guys here, wasn't c an unknown constant, right? A plus c, an unknown constant. Here it is an unknown constant, but it's an unknown constant that could be a function of y. Because if that was y squared, wouldn't its derivative with respect to x be 0? So it could work. If I do it over here, won't we get 1/3 y cubed? Don't know what letter of the alphabet, plus a constant, which I'm going to call k of x. Now, this function has to be this function. So it's kind of what you said, add. I'd probably use the word combine instead. I'm going to combine the information from here and here. And if I did that, would you agree that the function f has two distinct pieces? And as a check, couldn't I differentiate this with respect to x and prove you got that? And then differentiate it with respect to y and prove you got that? Okay. So far, so good. Right. Let's try another one. I think I've got 3 of these or 4 of these. How many have I got? Who knows? Here's another one. Bit trickier. Same problem, right? Excuse me, I'm going to just put you on mute. I'm getting some kind of feedback here.
That's me.
Okay, it's okay. It's fixed. Okay, here we go. Same problem, same strategy. A little bit trickier, but hopefully not too much. If you integrate this with respect to x, doesn't that here, this piece here, just is a constant, right? It doesn't really do much. So won't this get you x squared e to the y? Are you comfortable with the antiderivative that I used? Okay. Now, plus a constant that will be some unknown function of y, right? Because we integrate it with respect to x, the constant will have y's in it. We don't know if it's y cubed or 4 or whatever. Now, if you go the other side, this fella gets you y squared. And what does this fella get you when you integrate with respect to y? What does this get you?
X squared e to the y.
And then plus a constant. But when you differentiate with respect to y, won't the constant be a function of x? Now, I want to combine these two together to find f. I'll darn it in space. There's a little negative there that I missed in my question. What that negative is going to do is make this positive, right? Okay, now I've got it. I want to combine these two together. So let's see what we have. This guy is exactly the same as this guy. So I can be pretty sure that that's in the answer. What else have I got missing? Well, would you agree I've got this guy? So plus y squared. That's it. All I'm going to do is take these guys and we're done. So if this is correct, shouldn't I be able to differentiate with respect to x and I get that, and differentiate it with respect to y and I should get that, and I do, so I know I'm right. We're comfortable with this process of basically two different antiderivatives, and then you merge the answers, right? You combine the answers together to get a single function of f that has both features in it. But one last one. Here's our function that we're being asked to find. And this fella is 2x take away 6y. And this fella is negative 6x plus 6y take away 9. Okay. If you integrate this with respect to x, that piece gets you x squared. What does negative 6y get me?
Negative 6xy.
Right? Plus a constant, which is some function of y. So that's like just a placeholder, right? Call it in the letter of the alphabet, I like it, just call it that one. Now, integration with respect to y, this fella gets you negative 6xy. This guy here gets you what? 3y squared. This guy here gets you, I believe, negative 9y plus some function of x, right? A constant. And then you put the whole lot together. So you look at what you've got and you look at what you've got, and basically, if you cover these fellas up, because they're really just placeholders, and you merge these together, would you agree that you get that guy because it's common to both? And you need this fella, you need this fella, and you need that fella. Are you happy where all the bits are coming from? So that's a new skill that we've been practicing here. How to take two partial derivatives in terms of x and y and find a single function f where these are true. Are we good?
Just a
Yes.
quick question. Why isn't there still a plus c at the end of that? Because if you derive that with respect to f or x and y, it would still be 0.
So there could be a +9 here. Is that what you're thinking? Or a
Yeah.
plus something. Technically it is there, but we ignore it because in the fundamental theorem that we're going to learn about, the plus C's that you would normally put in kill each other off. And so it's a bit lax. They really should say plus C, but they don't, because we never use it that way. So we would consider this, and what I'm really answering here is a function that this is true for. And this is definitely a function that's true. And what you're saying is, but so is +3 and -11. And we're just saying, well, we don't really want to take care of those situations because you don't need to. But it was a good question. That's not a great answer, but the answer is, yes, it is there, but we pretend it's not, or we don't use it. Ready to move on?
Yes,
Yep.
just real quick though, if you were given a starting amount, we could find that C.
I guess you could, but we never ask you to. Yes, you probably could. I'm not saying I guess you could, you probably could. Now we're going to find out about a very special vector function or vector field. Now there are lots of vector functions, right? But not all of them are nice vector functions. So what do we mean by nice? Nice would be a vector field, a vector function that behaves in a nice, consistent way that we can deal with. The analogy would be, do you know if I went and said to you, I have a function f of x, and I said it was continuous? Wouldn't that be just another word for a nice function that doesn't do weird stuff? It doesn't have discontinuities. It doesn't have vertical asymptotes. It just is a nice curve, right? So we're looking at what you might want to call is a nice vector function. And nice vector functions are called conservative fields or conservative vector functions. Now, there are lots of ways you might describe a nice vector field. One of them you can't is using an idea of continuity. And the reason is that if you sketch one of these, don't you end up with a whole load of vectors pointing in all sorts of directions? Would you agree you can't really describe continuity now, because every single infinite point here has a vector associated with it, right? So we don't go the continuity route. We do go a very, if you were picking this, I don't think you'd ever come up with this. So what does a conservative field or a conservative function have that makes it nice? It has this. Take a general vector function, f of xy, and I'm describing it in terms of this here is like x squared y cubed plus y, and this is like e to the y plus x cubed, right? So it's a function, we'll call this guy p, we'll call this guy q, and p and q are typically functions of x and y. Now this vector function is said to be conservative, right, a conservative field, when the derivative of this with respect to y is equal to the derivative of this with respect to x. Would you agree that is probably not what you were expecting to be a nice vector field? Nice, a well-behaved vector field that doesn't do weird stuff, right? But that, nonetheless, is our description. So if you get a question and it says, is this function a conservative function or a conservative field? What you will do is you'll differentiate the first part with respect to y and the second part with respect to x, And if they are equal to each other, then you will say, yes, it is conservative field. And if they're different in some way, even just a little bit, you'll say, no, it is not a conservative field. And if it's not a conservative field, that's kind of the end of its life as far as 16.3 goes, because you can't really do anything that we're going to show you using the fundamental theorem of line integrals, because this only works for conservative fields. But doesn't the antiderivative thing really only work for normal continuous functions, right? You don't want to start integrating weird stuff, right? Some calc do. So far, so good. So let me pick a question that just asks, is it a conservative field or not? So here is our first example of that. Now, according to the naming scheme that I'm using, won't this guy be called P and this guy will be called Q? And the test is simply the partial derivative of the first one with respect to y and the second one with respect to x. Now notice it's not xy but yx, right? So this one is with y and this one with x. It's dead easy for me to screw that up. So be on the lookout for the next question where I may accidentally do that. Right, if you differentiate this with respect to y, would you agree you get x plus 2y? Happy with that? Now, what happens if you differentiate this fella here with respect to x? What do you get? Well, you get 3x squared plus 2y. Agreed? Is this a conservative field?
No.
Right, so nope. And the question's over. Let's see if I can find one which is a yes. Okay. So here is a vector function. And it's y e to the x plus sine y, comma, e to the x plus x cosine y. This will be P, this will be Q. So the partial derivative of P with respect to y. Well, if you differentiate this with respect to y, you get e to the x. And if you differentiate this with respect to y, you get cosine y. Great. And now we'll do the other one, but with respect to x. With respect to x, e to the x gets you e to the x. And with respect to x, you get cosine y. And in this case, would you agree the answer is yes, it is a conservative field. Cool. Would you agree that it's probably easier not to be a conservative field than it is to be a conservative field? So there are going to be a large number of, if you just randomly pick a function, a vector function, there's going to be a large number of no's, right? So we are only, for the most part, we are going to be more interested in the yeses. Because if it is a conservative field, a conservative function, it has a lot of properties that are quite unique and really useful. I'm not quite sure why they use the word conservative. It might just be from, you know, the old meaning of conservative, right? Something that's not too out there, right? It's kind of in the middle, kind of safe, right? Conservative. It might come from that, but it also might come from things like conservation of energy or conservation of momentum, in which
I
case,
think,
yes?
oops, sorry, go on.
No, I think, what were you going to suggest there?
The textbook says it has something, it represents the fact that the total sum potential or kinetic energy stays the same, hence energy is conserved, law of conservation of energy, hence conservative. That's what I think.
Ah, okay. So we're looking at some kind of vector field what has, for want of a better word, a lot of symmetry to it. Right, so the lines aren't just zigging everywhere, but there's a kind of, you know, flow, maybe a circular flow or a directional flow, but nothing too weird. Okay. Yes, Ben.
So in the previous section, we changed our units. I don't expect that we'll be doing this time around, but would it be possible to change the pretty much the area that you're graphing this to make it so it would be a conservative effect thing?
No, unfortunately, it would be nice, but no. Yeah, it would be so nice. Hey, maybe you can do it. Maybe you can find a way for that, a change in variable that could make it happen. We certainly don't do it. So, let me show you the next piece of the puzzle. If it is a conservative field, it has a number of properties. Here's one of them. If f is a conservative field, then there will exist a unique function f of xy that has the property that the gradient of f will equal this guy. So if you are a conservative field, then we can find a little normal function, right, a real valued function that has the property that the grad of f is equal to capital F. In these situations, this little f is called the potential function. Now, I know that word also comes from something to do with physics, like potential energy, but there's potential charge, there's potential all sorts of things, right? I believe potential means something to do with the difference between a start and a finish, right? So you're going to find that this fella here is a biggie. This little f of xy is going to be really, really helpful in finding the answer to line integrals and probably a whole load of things I don't know about. We got that one. So if it is a conservative field, then there exists a unique function f of xy that has this property. So far, so good. Now, still on this fella. If it is a conservative field, here's another property. If you find the line integrals, you know the f dot dr thing, right? That guy. You will get the same value as long as you start at the same and finish. So imagine this line integral C was using this curve to get from here to here. What the property says is that you'll get the same answer if you start from here, but you use that curve to get to it. And you start here and you go and you use that curve to get to it. It doesn't care what the curve is. You'll get the same answer for this line integral. So what matters is only where you start and where you finish, not how you get there. Interesting property. So you imagine going through a vector field, F, and you've got a point to start and a point to finish. What we're saying is that that line integral, which is basically the work done, right, and getting from one dot to the other, doesn't care how you get there, as long as you only start here and you only finish there, the answer to that line integral will be the same every single time. Does that seem reasonable, or is that kind of unexpected? So if you're a well-behaved vector field, this is true. Right? If you're a conservative one. Does it seem unreasonable, or does it seem kind of, nah, that doesn't make sense. I don't know why that's true, but it is. We good on that guy? Right. Still going. If F is a conservative field and you have a line or a curve starting at some point P and ending at some point Q, so can you imagine I'm calling this point P and this point Q, and P has coordinates AB and Q has coordinates CD, then that line integral is the value of little f at CD, take away the value of little f at AB. Isn't that very similar to that fella? Unfortunately, capital's a distraction. But isn't that end and start like in Calc 2? So this little f is like the antiderivative of the vector field. And that is actually what we call the fundamental theorem of line integrals. It's essentially this. We have another version of that same thing here. Suppose f is a conservative field and you have some curve C described by a parametric space curve, f of t. Then this line integral is f at the position B, take away f at the position A. And that essentially says that in a conservative field, line integrals are independent of the path taken. So somehow we're going to use this to find the value of a line integral. Okay. Well, some of you are writing, you want to say hi? Take attendance as well. Let's do our first example of using that property. Suppose I have a vector function, 2xy x squared, and that we're going to go from the point P with coordinates 1, 2 to the point Q with coordinates 3, 2. And I would like to find the line integral of this guy. Okay, so how do we approach this question? Well, the first thing we need to do is we need to prove it's a conservative field. Well, in this Well, it's a bit unfortunate these are called P and Q, but this is function P and this is function Q. And that tells me that if you differentiate this with respect to Y and you differentiate the other one with respect to X, shouldn't these be equal to each other if it's a conservative field? So if I differentiate this with respect to Y, I get 2X. And if I differentiate this with respect to X, I get 2X. Would you agree that that is a yes? It is a conservative field. So that would be the first step. Second step, we are now going to find little f for this function. Now, we know that delta f is equal to f, right? And we know that delta f is the partial derivative with respect to x and the partial derivative with respect to y. And we know in this case, it's that guy. Now, at the start of today, didn't I do some questions where we tried to find a function that had this property? So if I match it up, what do we know? We know that this fella has to be 2xy, and we know that this fella has to be x squared, right? And so if we work basically integration, then according to this, if you integrate this with respect to x, don't you get x squared y plus some unknown function of y? And if you take this fella, don't you get x squared y plus some other unknown function constant in terms of x? And in this case, didn't we get a really easy match? So I now know who f of x is. It's basically just x squared y. So far, so good. Now, the points that we are interested in is start and finish, right? Those two. Great. So, according to the fundamental theorem of line integrals, this line integral is just the value of f at the end, take away the value of f at the beginning. And since f is this function, what do we get? 3 squared times 2, take away 1 squared. Times 2. And this is 18, take away 2. And we have just calculated the line integral of this function, starting at P and finishing at Q. And do you notice that I didn't parametricize that? I didn't try and find a straight line between them. In fact, couldn't they have told me that you go from this point to that point and it went along the arc of some circle? And wouldn't I totally ignore that as well? Because as long as you have a start and a finish, it doesn't care how you got there. This cuts out the middleman and tells you the answer. And of course, that's step 3. Step 1, prove it's conservative. Step 2, find little f. Step 3, use that guy. Done. Ready for another one? Any questions? Last chance. Does it have a nice flow to it? Does it feel like you're going somewhere with it? And if you compare the normal ways of getting line integrals, can't they be a bit messy and fussy? Especially the integration part. in general, these tend to be a lot cleaner, which is why the method's even being used. Now, let's do another one. This is similar to 5. The function this time is x squared y cubed and x cubed y squared. And the curve this time is a space curve, and it's given by this fella. And we're going to go from 0 to 1. Okay, so we're being asked to find, you know, that guy, right? And let's start with, if I call this P and I call this Q, let's not. Can you trust me that that is going to be a conservative field? So can I just dot and save some time, right? So you can check it, but I bet you that ends up being true. That means I can now move on to step 2. I know that there has to be a function little f that has that property. And I know that that means that this has to equal that guy. If you use this fella first, then that, what does that give me? Well, if you integrate this with respect to x, you get 1/3 x cubed y cubed plus some unknown function of y. If you take that guy, he's going to be equal to x cubed y squared. And if you do this guy, if you integrate this guy, you get 1/3 x cubed y cubed plus some unknown function of x. And we got lucky again. Wasn't the answer just one term? So we now know the potential function. It's this fellow. Now, according to the fundamental theorem of line integrals, this line integral is the value of the function at the end, take away the value of the function at the start. So you might think, how am I going to get those? In the previous question, you were told, right? It started at 1,3 and it finished at 5,2. That's where this guy comes in. Now, that's going to be the start, right? And that's going to be where you end up. Now, if you plug 0 into here, you will get the coordinates 0, 0, right? In the space curve world, that's position 0, 0. If you plug in 1, you get 1 take away 2, which is -1, and 1 add 2 is 3, you get that guy. So do you see you've got your start and your finish points now? And so I just evaluate this function, the potential function at there and at there. In this case, it's 1/3 -1 cubed times 3 cubed, take away a whole load of nothings. And that, I believe, gives me -9. Do you like this method for calculating line curves? Is it less work or is it just different?
I think it's
Any-
less work.
I like it.
Okay, right.
I think it's easier work.
That's not a bad thing, right? Everybody,
Definitely like it more.
okay. So we're getting the feel for this. Obviously, the more practice, I've got time for just one last one, right? To do, but it's got that kind of 1, 2, 3. Although I'm skipping line 1 a lot now, you know, prove that it's conservative field, just to save time, right? But you know, I could have done it if you really needed me to. I'm just trying to find one that's kind of in the family that I've been doing. They're all. Okay, here's one. Took me a while to find one. So way over at 17. This is our guy. 8x y squared, 8x squared y. Can we just ... it is a conservative field? Because it is. Question 2 then. Let's find little f. So what do we know? We know that that guy is f. If you match them up, then this guy is going to be equal to 8xy squared. So that makes f, well, if you integrate it, you add 1 to power divide, I believe you get 4x squared y squared plus some unknown function constant in terms of y. And if you do the other fella, you're going to get, 4x squared y squared plus some other unknown constant in terms of x. I was hoping to get one where it wasn't always, you know, just easier, you know, pretty obvious who f is, right? Where there was a little bit of this and a little bit of that, but you get what you get. So that means that we now know the potential function, right? Now, the other part of this question is a space curve. And the space curve is t plus the sine a half pi t, comma, t plus the cosine of a half pi t. Okay, and t is going to go from 0 to 1. Just not really that interesting. Right, if you plug in 0 here, what do you get? 0 plus 0, you get 0. And if you plug in 0 here, you get 0 plus 1, you get 1. So that's this one. If you plug in 1, you get 1 plus the sine of a half pi, which is another 1, so you get 2. And here you get 0. So you can imagine I just plug 0 in here to get the x and y coordinate. Then I plug 1 in here to get the x and y coordinate. And so our line integral is the value of the function at 2, 0. Take away the value of the function at 0, 1. Oh, how boring can that be? It's 0. Okay, well, that's a version of 17. Oh, I just thought of something. If you have a conservative field, right, and you do your C, and your C, right, your curve, is a closed loop. That just means, you know, you start and finish at the same point, right? What do you know about the answer to that?
It's going to be 0 every single time.
Every single time. So if it's a conservative field and you do a line integral over a closed loop, right? You start at a dot, you zigzag everywhere you like, and you end up at the same dot. You are looking at a 0 line integral. So I wonder if that's part of being conservative.
I think it does, because if you're thinking about this as being a force vector, then you would be ending, if you thought about this as gravitational energy, you'd be ending at the same height. No matter how high or low you went, you'd always come back to the same height.
Right, so the overall difference is 0. I like that, right? I like that kind of, that makes sense in my brain, right? But magnetic fields and any other kind of field you want, if it's a closed loop, then the net effect is 0 because you end up where you started. So whatever energy you use to get there, you get it back on the return journey.